shortest path problems. And the problem of the day deals with a problem that might smell like a shortest path problem, or at least smells to me like a shortest path problem, but I haven't read it yet. It says, we're given, G is a weighted, directed graph where all edges have positive weights. A directed cycle is a directed path that starts and ends at the same vertex and contains at least one edge. Okay? So I guess just staying in one place doesn't count as a cycle. Okay? And it says, give a n-cubed algorithm to find the cycle in a graph of shortest weight. So let's look at this and see what we are dealing with here. We are given a weighted graph. This is a cycle. This is an example of a directed graph. There are weights associated with the edges, 20, 30. Let's say this was 100. This was 3. This was 2. And the goal here is maybe we're to find the smallest weighted cycle in this graph. That's what it says, the lowest weight cycle. What is the lowest weight cycle in this graph? Okay. Does anybody see one? I see two different possible candidates for the lowest weighted, well, two different cycles in this graph. Does everybody see that? There is the cycle that goes around like this, and there is the cycle that goes around like this, like that. Does everybody see that? Those seem to be my two choices of cycles. Is there any other directed cycle in that graph? You say yes, which one? You mean you want to think it goes around like this? The answer is there is no other cycle I see that respects the order of the directions. See, it's a directed graph. So a cycle has to be one that you can drive legally. Okay? And the question here is, how do we find the lowest weight directed cycle in a directed graph? Okay? Any questions about that? Things are happening on this machine, actually. But any questions about what the problem is? Given a graph, find the lowest weight cycle. How might we do it? Okay? What does actually, let's just put it this way. If we had a undirected graph, we could also ask what the lowest weight cycle is. But one cycle you'd have to be careful about ruling out would be a cycle that went to here, ka-chunk, and back. Right? Does everybody agree that that could be interpreted as a cycle on two edges? In a directed graph, we would be allowed to have that if we had edges that go in that way. Okay? Any questions? So how might we find the lowest weight cycle in a graph? Okay? Any ideas on how we might do this? Okay? And my immediate goal would be to try to, because I think designing graph algorithms is hard, I would be trying to let some other algorithm we know do as much of the work as we could. Okay? So any ideas on how you might go about trying to find the lowest weight cycle in a graph? Yes? Can we use a version of topological sort? Okay, so you hear directed graph. Directed graph, you may be thinking topological sort is a good thing to be thinking about. But what does topological sort do us? What kind of graphs does topological sort do its thing on? Acyclic graphs. Graphs without cycles. So if you could topologically sort it, you could certainly answer the question of what is the shortest cycle. The answer is there is none. Okay? But in general, the graph is not a DAG. Okay? So what block might we reduce this thing to? All right? Yeah. Okay, so you're saying use a DFS search and look for back edges. You are trying to invent an algorithm, is my way of looking at this thing. Okay? Somehow, algorithm design is hard, and I don't, and now you're thinking, well, I'm going to do that for a search, I'm going to do something special. Can you do depth first search on with weighted graphs? We haven't done anything with depth first search and weighted graphs, right? So I don't know. That's not what I would be thinking about. Okay? Any other ideas or leads as to what thing do we know how to do that might help us find the lowest weight cycle? What thing do we know how to do that sounds like part of lowest weight cycle? Anybody see anything? Lowest weighted what? Path. So what if I found the lowest weight path from S to T? How close am I finding? What do I need to do to find the cycle using that path? So long as I have an edge, okay, that goes back to, okay, either an edge or a path from T that goes back to S, then that would be completed for a cycle. Does everybody agree with that? So how might it says, give me an n-cubed algorithm to find a directed cycle of minimum total weight. Okay? How might we do this? Okay? Any ideas? What? What was that guy? Dijkstra or Floyd? Okay, Dijkstra. Let's say Dijkstra. Okay? Dijkstra or Floyd. Dijkstra could be used to tell me the shortest path from vertex 1 to everybody. And that took how much time? How much time did it take to find the shortest path from vertex 1 to everybody? N squared. If I do that from every vertex, now I have the shortest path from every vertex to anybody else. Does everybody agree with that? And that would take how much total time? N cubed. Does everybody agree with that? Now that I have this matrix of shortest paths, how could I, of shortest path distance from A to B for every vertex, how could I find the cycle of shortest length? Any ideas? I could use this thing? Okay. We know the cycle is going to contain, it says at least one edge, right? That means it's going to have at least two vertices in it, right? What if I did the following? What if I now tried for all pairs of vertices x and y? What is the distance from x to y plus the distance from y to x? Okay? If it's a directed graph, that's not necessarily the same thing. Does everybody agree with that? Directed graph, it's easy for me to get from here to there, but to get from there to this, I've got to go cruising through the full graph. Does everybody see that? But my claim is, if I did the minimum over all x and y of the sum of the distance from x to y plus the distance from y to x, doesn't that describe a cycle? That describes a way to get from x to y and back. That is a cycle. And if we try it over all pairs of x and y and took the pair that minimized this sum, that describes to me the minimum cost cycle. How many people see that? How many people don't see it and want to see it better? A couple people, okay? Let's think about this. The heavy lifting I think I want to do using my all pair shortest path thing, right? Whether I got it from Dijkstra or Floyd or whatever it is. Now I know the distance from the shortest path distance from I to j for all I and j. Okay? That's what this matrix gives me, right? The smallest cycle in the graph has the property that it contains at least two vertices, x and y, and is really the shortest path cycle that contains x and y. It describes the shortest way to get from x to y, and then the shortest way to get to y to x. Right? Suppose we used a detour. We didn't take the shortest way to get to x to y. I happen to know a nice detour to take. It's very scenic over here. Okay? If I took the detour, that would not describe the shortest cycle from x to y, right? The shortest cycle from x to y has to consist of the shortest path from x to y, and then the shortest path from y to x. Does everybody agree with that? And so now what am I going to do? I'm going to take the minimum over all x and y of what? The distance from x to y plus the distance from y to x. How much time is that going to take to compute this thing once I have that matrix? How much time does it take to compute the distance from x to y once I have that matrix? Constant time. Let's look it up. Bing, there it is. How much time does it take to compute the distance from y to x once it's in the matrix? Constant time. Bing, there it is. So how much time is this whole phase going to take? This phase is going to try all pairs of n, x, and y, right? How many pairs of x and y are there? N squared. Does everybody agree that this is really going to take n squared time once I have spent n cubed time to give me that matrix? Is that now clear? I think that's actually pretty convincing. And it should be convincing of a couple of things. It shows you the power of shortest path. Once learning how to compute, Dijkstra was a smart guy. I don't have to be a smart guy to solve these problems because I have Dijkstra's algorithm to sit there and give me the shortest path. Okay? But I can use it to solve more interesting problems, like this problem of the shortest cycle in the graph. Any questions? Questions? Oh, but I would like to do it at n squared m time. Is n squared m time better or worse than n cubed? Worse, okay? So you're saying you want to do a worse algorithm, okay? It's acceptable, but let's think of a different design. Can anybody solve this problem in something like n squared m time? Okay? Is there another question that we might be able to solve? Okay? Another characteristic of the shortest cycle in a graph. Here is our shortest cycle. I claim that there exists in any shortest cycle, in the shortest cycle in a graph, do we believe it will contain at least one edge? Of course it's going to contain at least one edge, right? Or else it's not very, it's got to contain at least one edge. That's what they tell me. Suppose I wanted to know, I have a particular edge I like that goes from x to y. Happens to have weight 105. What is the shortest cycle that contains that edge from x to y? What is the length of that cycle? Okay? We find out what the length of the shortest cycle in the graph that includes the edge x to y. There's a particular edge xy, right? What is the shortest cycle in the graph that contains that edge? What else do we need to make the shortest cycle that contains that edge? Need the return. And what is the return? What? The what from y to x? The shortest path from y to x. Does everybody agree with that? That if I want to know the shortest cycle that contains this edge xy, to complete the cycle, I am going to need the shortest path from y back to x. Does everybody agree with that? That path coupled with that edge gives me the shortest cycle containing that edge, right? How time would it take to find me the shortest path from y to x in a graph? N squared. Does everybody agree with that? That was our Dijkstra thing. And this would tell us for one edge what was the shortest cycle containing it. How could we find the shortest cycle in the entire graph? Try all edges. Does everybody see that? The shortest cycle in a graph contains an edge. Which edge does it contain? One of them. Let's try one of them. Try all of them, right? Take that edge, delete it from the graph, find the shortest path from its endpoint back to its start point, and minimize, and tell me what that sum is. I am going to minimize, to be precise, over all edges, ij in the set of edges, of what? The edge I to j plus the distance from j to I in the graph G minus the edge ij. Right? I have to delete that edge from the graph momentarily. Find the shortest path back. Okay? And this will give me my answer. Any questions about that? You believe that? Okay? Question. I am going to want to try all possible candidate edges as saying, this is your chance to be in the minimum cycle. How well can you do? Okay? To test that edge, what am I going to do? I'm going to rip it from the graph and then say, find me in the remaining graph the shortest path from what was its endpoint to its beginning, to its starting point. The shortest cycle that contained that edge consisted of that edge plus the way to get back to the start. Okay? Any questions about that? Okay? That should be believable now. How many people believe that? Or understand it? Let's even try understanding it. I think that actually shouldn't be too mysterious. A question like, I don't understand it yet, would be a good question. Okay? Because this is a good question of how you took what seemingly was a hard problem. You wanted to design an algorithm for it. Okay? But in fact, there were straightforward ways to do it, building on shortest path. Okay? Any questions about that? So I would be trying to build algorithms starting from the big blocks that you have, okay, is the instinct that you should have, rather than immediately start by doing a depth first search, okay, or saying by build an adjacency list and do something, okay? Any questions? Okay? Very good. Okay, so what I'd like to now talk about is we're moving into the section on combinatorial search, okay? And again, we motivated this last class by the problem of Sudoku, where somehow to solve a Sudoku puzzle, people, I think, how many people here had never seen a Sudoku puzzle before? One of you had never seen it, okay? Okay, you knew what it was, okay? I will confess I have never done one either, except I wrote a program to do it, okay? Any questions? So what is the idea? The idea was somehow that to solve this thing, we're going to need to try a lot of different combinations. There is not going to be a straightforward algorithm that will solve all Sudoku problems in a straight line, okay, is my argument. Or if so, you have to prove it works right. One algorithm for solving Sudoku that I know works right is try all possible configuration of numbers and test, is it Sudoku? Okay? Is it a superset of what I have now? Is it a legal Sudoku solution? If so, print it out. That is correct, although possibly slow. But on the other hand, if we search for the right solution, I claim we can search in a way that is both usually efficient or efficient for surprisingly large problems and guaranteed correct, because we're going to try all possibilities that matter. And that is the idea of backtracking. Okay? again, in the Sudoku world, okay, what we want to do is we use constraints to somehow prune our search so we don't actually explicitly try all possibilities. And backtracking is the idea that is the algorithm that enables you to do exhaustive search correctly and efficiently. These are the two issues that we're going to have. Any questions? Okay. So what is backtracking? Okay, and on one sense, again, I just told you a few minutes ago, don't do depth-first search. Essentially what backtracking is depth-first search, okay? So depth-first search, if you remembered what depth-first search is and understand depth-first search, you will understand backtracking, okay? What backtracking is a way to, but what's going to be different about backtracking and depth-first search, just to sort of give you the whole picture right now, is that in depth-first search, we've assumed we had the entire graph stored in our computer. In backtracking, in some sense, what we're doing is depth-first search on a graph that doesn't completely exist. What we're going to do is build the graph as we need it, okay, as part of our search. That is really the big idea. Maybe this will be clearer after you see the implementation. But that is really the quote-unquote big idea here. What we're going to do is backtracking is a general algorithm, okay, which we have to customize for every different application. Sudoku is an application. 8 queens is an application. Bandwidth, which you will become familiar with at the end of this class, is an application, okay? In general, what we're going to do, though, is there is a basic engine that is in common to all these applications. And it involves basically taking the basic ideas. We're going to build up a solution piece by piece, okay? Every time we think we have a way to extend our solution by more, make it bigger, put another piece into the solution, we're going to do that. We see another way we can make the solution bigger, we'll do that. When we run out of any ways to make our solution bigger, have more pieces, we know that that meant that we can't complete the solution from here. We must have made a mistake with something we put down before. And we're going to backtrack, remove that piece, and try something different in its place. Let's think about Sudoku. How would you solve Sudoku like this? You've got, I claim, a Sudoku board consisting of slots. There's certain slots that are already filled in, those we don't care about, right? To complete the Sudoku board, you're going to have to put a number in each slot that remains. Okay, do people see that there is a notion of slots that are open in a Sudoku board? Originally, if there were no constraints, the numbers 1 through 9 could appear in this square of the Sudoku board, right? We put in a 1, and then we say, okay, that's good. Let's now try to fill the spot next to it. There's going to be a set of numbers that are possible. Let's pick the first of these numbers. In the next spot, there's a set of numbers that are possible. Oops, there are no numbers that are possible. That set is empty. No matter what number 1 through 9 we try to put in, it caused a conflict, right? What does that mean? We made a mistake so far with what we tried to put in. So what are we going to do? We'll unmake this mistake by deleting the previous thing and go down and take the next candidate from that list and keep searching. Okay? The claim is that if we ever march far enough that we filled in a number in every slot, ding, 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 we have solved our Sudoku problem. If, on the other hand, we back up here and we've exhausted all possibilities, then Sudoku, there's no way to fill it in. Okay? Is that clear that that's the systematic search idea? Okay? Any questions here? So with backtracking, what we're going to do is keep track of a solution vector. What is the solution vector? It is an array, a vector or an array. I think of them as the same thing. A solution is going to be a set of slots where the ith element in this array was selected from a set of candidates, S sub I. The vector might be an arrangement, let's say, where it's this is describing a permutation, or it might be, in the case of Sudoku, a string of numbers. Okay? The important thing here is that what we're going to do is at every point we have a set of candidates for this slot. And we're going to put one down, work out the consequences. When we get back to the point where we delete it, our next step is to put the next candidate in from that set. Okay? And by doing this, we will systematically evaluate everything. Any questions? Any questions so far? Okay? So again, what's the idea? At each step in backtracking, we start with a partial solution and try to extend it. After we extend it, maybe it is now a complete solution and we should report it. If so, good. If not, we should check whether, if it's not a complete solution, our goal is to check, can it be extended? Are there active candidates for the next spot? Okay? If so, keep going. If not, we made a mistake. Delete the last element from it, and then try another possibility if one exists. That is backtracking. Any questions? Here is the algorithm. I'll show you the algorithm, and I'll show you the program. They're basically the same thing. What is the recursive backtracking algorithm? A is our solution so far. K is telling us how many slots have we filled in. In Sudoku, you have 56 slots left on the board that weren't filled in, right? There's 56 potential slots in this array A. We're going to first fill in the first, then the second, then the third. K tells us how many slots have we already filled in. We test, is our partial solution so far a complete solution that we want? Is it a filled-in Sudoku board that is beautiful? If so, print it. If not, go down to this thing. If it's not a complete solution, there's got to be a way to extend it. So let's bop K up to K plus 1. And now compute the set of possibilities for the new kth position. What numbers, what values might possibly sit in this new kth slot? These are filled in. Given what's been filled in so far, what positions, what values might be possible for that spot? Once we have that set of possibilities, then one by one go through this set. Take an element out, stick it in the kth slot, delete it from the set of future possibilities, and search from there. If in the course of this search, recursively, it finds a solution, great. If not, it's going to come back here and loop back and say, well, I couldn't find one. Well, the set of possible positions of the kth thing is not empty. Take another one out, and let's try it. Stick it in the kth position, and search from there. Any questions about that? Yes? SK is the set of possible, we'll talk about that more later, but this is important, possible values for the kth slot. Well, you're growing the solution piece by piece, right? Let's think about Sudoku. You have a Sudoku board that is partially filled, right? Some of the numbers came to you because they came with the square. Some of them maybe you already filled in, a 1, a 7, a 9. This spot, the fourth spot, k equals fourth spot in this array, corresponds to a square on the Sudoku board, right? What possible values are there at that value position in the Sudoku board? Let's take an example. Boom, 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 boom. What possible values are there here in this for this slot? What could there be? Are the possible values 1, 2, 3, 4, 5, 6, 7, 8, 9? Or is it a smaller set of possible values? Which possible values are there? Can it be 1? No, because it's in the same box. 2? No. 3? No, it's gotten over there. 4? 4 looks good. 5? Yes. 6? No, I see a problem with 6. 7? See a problem with 7. 8 is a problem. Right? Is 9 a problem? So what are my set of possible values here? It's 4, 5, and 9. Does everybody agree with that? Which is the right one? It's 9. How do you know it's 9? Because it says so on my solution. But if you don't have the solution, do you know? No, you've got to search. All of them are possibilities. Which is the first one you're going to try? 4. 4 is a good candidate, right? And what happens when you search putting that one in 4? What is going to happen? Eventually you're going to hit a point where there is a square that is empty, but there's nothing to put in it, right? At that point, you've got to step back. You've got to backtrack and start erasing things and try other possibilities, right? And eventually, you'd get back to this position and say, 4 isn't going to cut it. Let's try 5 and work out the implications of 5 ahead. And eventually, it's going to run out of gas. There's going to be a square where there isn't a possibility. And then you're going to say, 5 isn't it. The only remaining possibility I have is 9. Let's try it. And in fact, that will be acceptable. There is a way to continue it from that. Any questions? So that is what, go back here, boom, 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 boom. That is what this S stands for. It's the set of possibilities. Any questions? Yes. You're saying you're saying that because there is a way to solve it, if God was playing the puzzle, there wouldn't be any mistakes made, right? Okay? God, the Creator, could do this in pen. Does everybody agree with that? Okay? Well, fine. But the question now is, either you've got to figure out how the Creator is doing it, or you have to say, I don't know how to do it exactly, but I know that if I try all possibilities in a systematic way, I won't miss the solution. And that is our philosophy here. The philosophy is we're giving up on a smart way to do it without mistakes. Instead, what we're saying is we're going to search through all the possibilities, but in a clear enough and an efficient enough way that we don't get into, that we'll still get a solution reasonably quickly. Okay? Any questions? If you take actually an automata theory class, maybe what you look at is the difference between a deterministic and a non-deterministic way of doing it. You're sort of thinking in a non-deterministic way. What if the answer was magically pointed out to you each time? That doesn't work. In practice, we're going to have to search. Okay? But if we do the search efficiently enough, we can solve surprisingly large problems just by doing this semi-blind search. Yes? Okay, so you're saying that in fact what you are doing, saying that when you as a Sudoku solver, you are backtracking. You're saying, hey, I'm doing the same algorithm. That's exactly right. All those people who are solving Sudoku problems, you are solving as purely a backtrack automata. Okay? and if that makes you feel good about yourselves or not. But that's basically what you're doing. Okay? Even more interestingly, the puzzle was probably designed by a computer. So the computer is giving you work to doing the brute force search. Okay? But that's exactly what you're doing. That's why it's a good example of backtracking. Okay? Any questions here? Okay? In the book, I work through a complete Sudoku program. I encourage you to look at that one. We're not going to talk about that in here. Okay? But it's the basic idea is what we're doing here. It's just another example of backtracking. Any questions? Oops. Okay. Let's go take a look at this thing. And as I was saying here, is that when you think, what is backtracking? Philosophically, what it is going to be is a form of depth-first search on a graph that is implicit. There's sort of the state of vectors. Here's one way to think about it. Think about a graph where the vertices are partially filled in state vectors. Right? There is an edge from one partially filled in state vector to another if there is one more slot that is filled in this vector than in that one. If they share the prefix in common. And this one has one more number filled in, right? This state is somehow reachable from that state. And what we are looking for is ultimately finding a path to a state which is where it's all filled in, right? Backtracking is nothing more than depth-first search on the graph where you're starting from the state where every vertex is where no slots are filled in to a vertex where everybody is filled in. Okay? Any questions about that? Okay? Any questions? Here is my Sudoku program. My backtrack program. Okay? And it's an exact implementation of this algorithm in C. What is the key idea? Let's read it. Backtrack takes as input a solution vector A, just an array. K tells me how many spots have been filled in. And there may be some problem-specific input to the problem. If it's a Sudoku problem, maybe there's a Sudoku board I'm carrying around. Right? What are my variables? There is an array of candidates for the next position. There is how many candidates are there for the next position. Right? Because, it may be that the array is of size maximum number of candidates. Maybe, in fact, only the first 3 values of that array will be meaningful. What are we doing? We are calling a few application-specific routines. Let me circle them. Here are 3 application-specific routines. All the Sudoku-ness is going to lie in these 3 routines. One is, test is a partial solution, A, K in the input. Is it a real solution? Okay, it returns true if it is a real solution, false if it's not. Process solution says now that we have found a solution, tell me what to do with it. Maybe if it's Sudoku, you want to print it out. Okay? Maybe you just want to count how many solutions there are. So maybe just add 1 to the count of solutions. Or maybe just print out, haha, I found the solution. That is done by this routine process solution. Otherwise, what do? We didn't find a solution. Let's now try another spot, the K plus first spot. Construct what candidates are there given the current state of our vector and the input. Tell me what spots elements there are for the kth position. And store that in this array n candidates. Okay, C and n candidates. Then what do? For each one of these candidates, okay, copy the ith candidate into the kth position here. Now we've increased the size of our partial solution. Backtrack from here. And keep going and hopefully find something. If you didn't finish, if you didn't find something, go back and try a different candidate. Any questions about that? How is this like depth first search? What does depth first search do? Okay? Doesn't depth first search say, hey, I found a vertex. Let me loop through all outgoing edges from that vertex, right? And for each edge, once I go there, start my search recursively from there. Isn't that what depth first search did? This is just like depth first search. The edges here are the candidates to try to another vertex. Any questions? Okay, any questions at all? Your job for any backtracking application, be it Sudoku, be it bandwidth, which you'll do a little late today, is to write a program for is a solution, process a solution, and construct candidates. And then it does the search for you. Any questions? Okay. So what are these guys? Again, I told you, is a solution is just a Boolean function that tests whether the first k elements represent a complete solution. Okay? I give you a partial vector. Is it something that's complete or not? For a Sudoku program, how would you tell whether or not my partial vector is a complete solution? Okay? How would you tell if I give you a set of numbers here? Is it a complete solution? So there are a couple ways I might do it. One possibility is test whether or not all the rows and columns, stick all these numbers in, and test whether all the rows and columns are satisfied, right? That would be one way I could do is a solution for Sudoku. What might be a simpler way? Suppose I only put a number into the vector if it didn't cause any contradiction so far, right? Remember, my candidates for here were candidates that didn't have any contradictions with anything so far. If so, how could I tell whether or not my set of numbers here is a Sudoku solution? Just check the length, right? If, in fact, I have filled in every slot on the Sudoku board, I didn't have any contradiction here or 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 here. If k is equal to the size that I want, this must be a Sudoku solution. People get that idea? Could be as simple as that to test whether or not I have a solution. Okay? Construct candidates. How would this is a routine that given a partial Sudoku board, whatever the input is, a partial vector, and whatever the input was, tells me what are the candidates for a particular slot. How would I write construct candidates for Sudoku? Suppose I want to know what the candidates are for this ijth square of my two-dimensional matrix. What are my set of candidates for a partially filled in Sudoku board? How would you do it? So I'd say 4i goes from 1 to 9. Okay, I did it just so I had set up a bit vector of numbers. All of these guys are so far possible candidates. I then said for any of these numbers, what numbers are there in my row? 3 is, turn that to a false. 6 is, turn that to a false. Look in my row. 5 is there, false. Who's in my box? 2 is there, false. Then 4i goes from 1 to 9. If it's true, that is a candidate. It still hasn't been ruled out. That is a candidate. And that's as simple as what I have to do. Anybody who has not been eliminated so far is a candidate. Okay? Any questions about that? Again, look at the book. That's a 20-line program. It's nothing more than that. Okay? And those will give me the set of numbers that are legal for this square. Any questions? And what's the final thing? Process solution. Basically, now that you have a solution, what do you want to do with it? Print it out, do something with it, right? Any questions? Those are the three things that you need. Why is this going to give us a correct algorithm with those three things? Backtracking will guarantee us correctness because we are explicitly trying every possibility, potentially, for every slot, unless we find that there is a problem. Okay? I claim it also gives us some level of efficiency because we're never going to visit any state more than once. Let's consider the partial state 1, 3, 4, 5. How did we get there? We had gotten to the state 1, 3, 4, and we had tried all possibilities for the next spot, one of which happened to be 5. Right? But once it backtracks, we're never going to try anything with that prefix again. That's the key point here, right? We're never going to go back and say from 1, if we keep backtracking, if we backtrack past this, that meant 5 didn't work. Are we ever going to go stick 5 in there again and say, try it again, maybe it'll work this time? Well, 5 might be in that slot, but not with the same prefix. Of possible solutions. We've tried that prefix. It didn't work. We're going to move to a different prefix. Any questions? Okay. Any questions? Okay. One other little thing, just because recursion is magical. Remember that with a recursive thing, what are we going to do in a depth first search? We're going to call backtrack with k equals 1. And then it's immediately going to call backtrack with k equals 2. And it's going to construct candidates and call it with k equals 3, k equals 4. Because of recursion, there is a stack of partially completed backtracks. Do people see that? That's what happens in any recursive call, right? The set of candidates is a local variable in each call. So when we stick another candidate in here, in our slot, and call more backtracks, our state is still sitting there. And once we have backtracked from all this stuff, the set of candidates at that level is there, ready to be resumed. Okay? Just like it is at any other recursive call. Any questions? Okay. Good. So let's write an algorithm, a backtrack program, to enumerate all subsets. Okay? There are two main combinatorial things that you see: subsets and permutations. A lot of problems reduced to one or the other. How many subsets are there on n things? How many subsets are there on 3 things? Let's take a look at this thing. Let's make sure we understand this. How many subsets of 1, 2, and 3 are there? Somebody. How many subsets? You say 6? Anybody else? I hear 8. How many do you have? Okay. You say, well, you can't count it. You said what? 9. I hear 2, 8, and 3, 6, 8, and 9. Okay, that sounds like a backtracking problem to find the right one, right? Let's instead count that. What are the subsets of 1 through 3? I think that there is a subset of that is completely empty. Does everybody agree the empty set is 1? How many subsets of size 1 are there? 1, 2, 3. How many subsets of size 2 are there? 3. 1, 2, 2, 3, 1, 3. Does everybody see that? How many subsets of size 3 are there? 1. How many are there? 1, 2, 3, 4, 5, 6, 7, 8. Does everybody see that? How many are there of size 4? 16, twice as many. Why are there twice as many? Anyone give me an argument for why there are twice as many subsets as you bop up n to n plus 1? Why is it double the number of subsets? Everybody see that? What? Well, it's because it's a 2 to the n function, but let me argue, I'll give you a proof that it's a 2 to the n function. If I want to make all the subsets of 4 elements, I claim I could do it as follows. Take all the subsets of the numbers 1 through 3. Those are all subsets of the numbers 1 through 4, right? Which ones are missing among all the subsets of 1 through 4? If I take just those 8 things. Okay? Which subsets of the items 1 through 4 are missing if I just take these 8? The subsets which contain 4. Which are the subsets that contain 4? They're exactly the ones that don't contain 4, with 4 added to them, right? Everybody see that? There's 8 green subsets, and 8 green subsets with 4 stuck with them. And together that covers all the subsets of 4. How many people believe that now? Feel in their bones, they see why that is, okay? A question like I don't see it is a good question. Any questions? So what is interesting here? What I'm going to claim is the reason why that works is we could represent a subset as being a array of n elements, each one of which is true or false. Suppose I have the vector true, false, false, true, false, 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 true, true. What subset could that be taken as being? Suppose I let a sub I is going to be true if and only if I is in the subset. This true would mean that 1 is in the subset. This false means 2 isn't. 3 is, 4 no, 5 no, 6, 7, 8 yes, 9 yes. Do people see what I'm doing here? Any subset I claim can be described as a bit vector, a vector of trues and falses, of whether that value is there. Do people agree with that? Let's think about that. Suppose I want to represent the vector, the subset 2, 4. What would be the bit vector that would correspond to the subset of elements 2, 4? What's the first value going to be? Second value? Third value? False, true. Do people see that? There is a one-to-one correspondence between bit vectors on n elements and subsets of n elements. Do people see that? How many people see that? How many people don't? That's an argument then of why there are 2 to the n. How many bit vectors are there of n elements, each of which is true or false? How many? 2 to the n. 2 times 2 times 2 times 2. How many subsets are there on n elements? 2 to the n. There's a 1-to-1 correspondence. Does anyone remember the big word for 1-to-1 correspondence? Bijection. Bijection, okay? I don't remember what those words mean, okay? So it beats me. But it's clear to me that there is, for every set of subsets, for every bit vector, there is a subset corresponding to it, right? So if we count through all the bit vectors, is that the same as counting through all the subsets? Yes. So what is my program going to be to backtrack through all the subsets? I need to give you 3 subroutines. One is it a solution? When is a bit vector on n elements a solution to a subset of 2 to the n, of n elements? Namely, when all the slots are filled in. This is one of my 3 routines. Everybody see that? It will say, yes, you have a solution when all elements in your bit vector are filled in. That wasn't so hard. What are the set of possibilities for the kth slot of my bit vector? What are my possibilities? True or false? Is that what I'm doing here? The first possibility is true. The second possibility is false. There's 2 possibilities. And that's basically all I need. I need something to process the solution. Once I have a filled-in bit vector, true, false, false, true, true, how do I get the subset from it? You kind of think the subset for this really is 1, 3, 5, right? That's the cool thing to print out. If you start your indices from 0, that's, again, I started them from someplace. Whether I started from 1 or 0, I did. Okay? But what am I saying here? For I goes from 1 to k. If a sub I is true, print out, actually I didn't really say it, print out I. Okay? And that would then print out the numbers that are in the subset. Any questions about that? Those 3 routines are all I need to generate all the subsets. Okay? Any questions? Let's trace through this for a second. Oh, and this is basically the main program. All I'm going to do is now have it to generate subsets on n. I am simply going to start backtracking where I start with an empty vector. Okay? Because there's nothing in it so far, right? Yes? I claim it doesn't because I tested it. But this is an index thing, that these things are tricky and hard to figure out. But I think I'm starting with my index is equal to 0 here. Because there's nothing filled in the slot so far, right? Then when I went back to my backtracking, I started out, if you look at my backtrack routine, I start out by incrementing my counter. So 0 became 1. And I look for the candidates for the first spot. So I claim I'm not having a problem with indexes. Okay? Any questions? You wanted to start it from 0, you could have done it. But you have to change it a little bit. Any questions? Okay. Let's see if we understand this. Okay? Let's now trace through and see what would this backtracking program do. Let's execute it. Let's say we want to find all the subsets of size 3. What will we start out with? We have 3 slots. K is equal to 0, right? Now what are we going to do? K goes 3 plus 1. We're interested in the first slot. What are the candidates for the first slot? True and false. What are we going to do? We're going to put a candidate in the first slot, right? Which one are we going to put in? True, take it off the candidates. Now what are we going to do? Call backtrack again. Go over to this spot. What are the candidates for this spot? True and false. Does everybody see that? What am I going to put in the first slot? True. And now what am I going to do? Advance again, right? What are my candidates for this slot? True and false. What am I going to put in it? First one, true. I'm now going to go call process solution. Now, is this a solution? It's full, right? So this is a solution, ding, ding, ding. What subset does that correspond to? 1, 2, 3. Does everybody see that? Let's say I want to keep going and get all of them. What am I now going to do? What's my next step? Backtrack from there back to here. Let's try a different candidate. That's a false, right? Go forward. What subset is that? It's got all 3 elements filled in. Ding, ding, ding. It's a solution. What solution is that? 1, 2. Great, backtrack. Try another candidate for this slot. What other candidate is there for this slot? There is none, right? I have to backtrack again. What am I going to put in that slot? The F. Now there's an F in there. Does everybody see that? Maybe you don't see it, so let's write it in another color. Now you see it, maybe. What are the candidates now for the third position? True, false. Does everybody see that? True, false. Which one am I going to put in? Might as well put in a true. Ding, ding, ding. What subset have I realized? 1, 3. Backtrack. Put in the false. What subset is that? 1. Do I have any other candidates for here? For the third slot? Nope. Do I have any other candidates for the second spot? Backtrack, backtrack. I overwrite the first position now, right? What are my candidates for the second position? True, false. Okay. I put in a true. Let's get rid of my green. And put in a true. Now what are my candidates for the third spot? True, false. Put in a true. What's my subset? 2, 3. Okay, I put true. Now what's my next candidate? Put in a false here. What's my subset? True. Anything else for this position? For the third position? Nope. Anything else for the second position? False. Let's go back and do true, false again. Put in a true. What subset is that? 3. Replace that, put in a false. What subset is that? What? Empty set. Is there any other possibility for the third position? Is there any other possibility for the second position? No. Is there any possibility for the first position? No. Okay? These are the subsets, and those are the orders that I encountered them. Do I have 8 of them, I hope? 1, 2, 3, 4, 5, 6, 7, 8. Any questions? Now, some of you felt maybe it seems boring to do backtracking by hand. Well, if you feel that way, why do you do Sudoku puzzles? Okay? Any questions here? Okay? Any questions about why this routine works? Okay? Fair enough. Let us do one other special case of backtracking, another simple case, which is the case that is actually going to come up in your problem, your programming assignment. Okay? Suppose we want to construct all permutations. How many permutations are there of n elements? N factorial. How many permutations of 3 things are there? 3 factorial, which is what? 6. Does that make sense? What are they? 1, 2, 3, 1, 3, 2. 2, 1, 3, 2, 3, 1. 3, 1, 2, 3, 2, 1. See what I mean? 3 factorial permutations? 6? Any questions? So how are we going to construct all the permutations systematically? Well, we need to do 3 things. We need to construct a permutation. permutation, the candidates for a new slot. We need to test, is it a complete solution? And we need to print it out, right? Suppose we represent our permutation by the numbers we filled in to each slot, right? Suppose we have a permutation on n elements. What are the candidates for the kth position of that permutation? What numbers could there be? We want a permutation here on 4 elements, right? What are the candidates for the third spot? 2 and 4. Does everybody see that? Those are the candidates. Why couldn't it be 1? Permutation would have a repetition, right? Why couldn't it be 5? Because, well, there's not room for 5 elements, right? So how could we construct the candidates for the ith position, the kth position? What does it mean? It is basically testing all the numbers from 1 to n and asking, are you in the permutation so far? If you are, you're not a candidate to go in again. But if you're not in the permutation so far, let's stick you in as a candidate for the next spot. Is that believable? Again, you could read this more carefully offline, but basically this is the code for doing that. Okay? Any questions? How do you tell whether or not you have a solution? When do you have a complete solution? If in every spot you put in a number that hasn't occurred before. When do you have a solution? When do you have a permutation? When all the slots are filled in, is that right? And that's all it's testing here. And finally, given that I've got a vector that says 1, 3, 4, 2, what do I print out that solution? Well, 4i goes from 1 to n, print it out. Okay? Any questions here? Constructing the candidates was a little trickier here, but still not rocket science. Does everybody agree with that? So again, my claim is that if you can do these 3, break your problem down to construct the candidates for the next spot. Test, is this a partial solution? Okay? And then print it out. That then is your complete solution once you have backtracking. Any questions about that, about how the backtracking works? I encourage you strongly to go through the backtracking and look at it for the case of permutations. Make sure you understand why that works, what order it prints things out in. Any questions? Okay, the thing that I want to get to, we've got 10 minutes left. I want to get to, we're going to cruise ahead. There's other things here, but that's more just examples that might be interesting. Oh, no. Okay? I want to talk to you about your homework 4, which is the programming contest, programming problem. And you're going to be asked to solve an optimization problem on graphs called the bandwidth problem. What is the bandwidth problem? Okay? It has nothing to do with network bandwidth, okay, by the way, so don't get that out of your head. But what it has to do with is a problem. It's a problem on drawing a graph on a line. Okay? So, suppose we have a graph, and we take the vertices and permute the vertices. Give me an ordering of the vertices. Does everybody agree that if you give me, let's look at this example here. Here I've got a graph. I've got an ordering of the vertices numbered here from 1 to 8, right? Any edge, if there is an edge from 3 to 6, there's an edge from 3 to 6. How long is that edge if we draw these things as equally spaced numbers? Okay? How long will it be? 3. And why is it 3? It's because 6 minus 3 is 3, right? Does everybody see that if you give me a permutation of the vertices of a graph, every edge will now be between 2 vertices, right? Every edge now has a length in terms of how many permutation elements there are between it. Do people see that? Our goal is to find a permutation of the vertices which minimizes the maximum length of an edge. Look at this permutation. This is a really nice permutation, right? It has the same graph, actually. There is an edge from 1 to 8. 1 to 8 are next to each other. From 8 to 2, 2 is next to each other, right? If you trace through it, you will see that every edge here is of length 1, right? Does everybody agree that for this particular graph, this permutation gives you a longest edge of length 1. Do you see what that is? Your job is, for a given input graph, to find what is the permutation that minimizes the length of the longest edge. Okay? Any questions about what this problem is? Okay? Can anyone give me an algorithm to solve this problem? I want a correct algorithm to solve this problem. Yes. Try every permutation. Does everybody agree that one way you could write this program would be for I goes from 1 to n factorial, construct the ith permutation. Then, given the original graph, for every edge in the graph, there's an edge from ij. Look up what is the position of I, what is the position of j, subtract them, and if this is bigger than the biggest edge I've seen in that graph, add that as my potential bandwidth. Does everybody agree that that algorithm will work correctly? How many people understand the problem well enough to see that that will work correctly? How many people are confused by what the bandwidth is? Okay, a couple people. Okay? Let's try an example here. Let's say we want to find the bandwidth of, here's a graph that maybe is more interesting. 1, 2, 3, 4. Okay? Actually, let's make it a little bit more challenging. 4, 2, like this, right? If we lay out the permutation 1, 2, 3, 4, what are the edges going to be? There's an edge from 1 to 2, from 1, no, take it back. Let's try this exam. Is there an edge from 1 to 2? No. Let's do it in red. There's an edge from 1 to 4. There is an edge from 3 to 4. There is an edge from 2 to 4. Does everybody agree with that? That would be a permutation. What's the length of the longest edge here? 3, right? Is there a better permutation than that? Someone want to suggest a better permutation? You say 1, 4, 2, 3. So what would the graph look like then? 1 goes to 4, 4 goes to 2, 4 goes to 3. Now what's the length of the longest edge? 2. Does everybody see that? This one's better. Okay, can anyone do better than that? Can anyone lay it out so the longest edge is of length 1? No, no way to do it, right? 4's got to have, everybody's going to be of length 1. All 3 vertices have to be buddies of length 4. They have to be immediate neighbors. There's only room for 2 neighbors, right? So your job is, as input, to take a graph. You guys already know how to read a graph as input, right? If you did the homework that's due today, right? Your job is to take as input a graph, try all permutations, okay, and find the one that minimizes the length of the maximum edge, okay, and that is the bandwidth, okay? Any questions about that? So you could do this. Your job, again, the homework is posted on the web. Okay, I always told people like things on the web these days. You don't need a printout. Okay? But it's, what you will be asked to do is if you go to the web page, you will see about this assignment. It will tell you where to go for graphs. Your job is to write a program that reads the graph and for any graph calculates its bandwidth. Okay? And your algorithm has to always give me the absolute best permutation. Okay? And the goal is to see what is the largest graph that you can answer correctly. Okay? If you try all permutations, how many permutations are you going to be trying? N factorial. I like to think that 1,000,000 is a nice number of things to be done by a computer. A computer can do 1,000,000 things in maybe it's a second, but it starts to be time. Okay? Depends what things you ask it to do. What value of n is it that you get to be 1,000,000 for n factorial? What's 10 factorial? Who knows? It's about 3,000,000 if I'm correct. It's approximately 3,000,000. Okay? A chunk like that. So if you write a program that tries all permutations, and I just gave you the code for it, right? You can go to the web page and follow a link and get something that will give you all permutations. And just test. You will have a correct program for bandwidth. But I claim it will not, it will die. Okay? It won't come back. It won't return an answer. Once you get too much past 10 vertices, maybe it'll be 15, but it's going to hit a sudden wall, I guarantee it. Okay? Your job is to try to be as clever as possible and come up with the fastest program that is correct. Okay? Any questions? There will be a prize awarded to the fastest program and to the slowest program. You don't want the prize from the slowest program. Okay? Any questions about what the assignment is? Okay? If you get your act together, you can write a solution in probably 50 lines, especially if you use my routines. Okay? But now, again, and if you do the best solution, it's actually not going to be incredibly long, but I claim it's going to be smart. Okay? And we'll look into exactly what smart means as of next class. Any questions about that? Any questions about the assignment? Question? I said it is due on the date that it is on there. I don't remember if it's the 7th. It's due after break. Okay, is the first criteria. Okay, any questions here? Okay, I encourage you to look at it. I even encourage you to actually try to get a 0th order solution written as quickly as possible. And then spend the time doing the optimization to make it fast, because that's the interesting part. Thanks for your attention. See you guys next class.